Hi everyone, in this video I would like to explain the QQ plot. So Q stands for quantile function, that is the inverse of CDF, cumulative distribution function. And QQ plot, so we have two QQ, so we compare the two quantiles. And the QQ plot is used to check if observations are distributed normal, or in general that we can check if observations are distributed as a specific function. Okay, so the definition. So let x1 to xn be ordered observations, so smallest to largest, and f be the hypothetical CDF. So usually we use the normal CDF to check normality of observations. Then the plot, the f inverse of I over n plus 1 xi. So this is called the QQ plot. If we have n observations, we have the n points defined by this, I is equal to 1 to n, and this is called the QQ plot. If f is normal, we say this as a normal QQ plot. We start with an example. So suppose that we observed 4 observations, -1, 0.1, 0.5, and 1.3. And we would like to see if these observations come from normal. Such assumption is plausible or not, we would like to see. So then we check, okay, so by definition of QQ plot, basically we plot these 4 points. So these are ordered observations, -1, 0.1, 0.5, and 1.3. And x coordinates are f inverse of 1/5, f inverse of 2/5, f inverse of 3/5, 4/5, and 4/5. And the quantile function, so f inverse, can be used to generate random numbers. So we would say that if we have a random number between 0 and 1, and we calculate f inverse of that random number, it's actually the random number which follows the distribution f. And if we generate those numbers, so okay, so if we follow that rule, then we can actually generate the distribution f. Okay. Then now that we think about what's the typical realization of 4 random numbers which follows distribution f. Okay, so if we pick up a number randomly between interval 0, 1, and we think about f inverse of that value, that is a random variable. So that means if we have 4 observations, one typical realization is, okay, so you plug in just the 4 numbers which have equal interval in interval 0, 1. Then 1/5, 2/5, 3/5, 4/5 is a reasonable expectation, our reasonable expectation for random numbers, right? So and if we have this as x coordinate and the actual observations as y coordinates, basically, so these points, these values are similar, we can expect. Okay, so this is the smallest observation out of 4. And this is the smallest observations for typical realization of 4 random numbers, which follows distribution f. So if the original observations, these 4 observations follow distribution f, then these points are almost on the straight line y is equal to x. So if almost y is equal to x, on y is equal to x, we can say these random numbers can come from the distribution f. If it's much different, then that's an evidence against the fact that observations follows distribution f. So in general, if the observations come from the hypothetical distribution f, approximately the capital F of xi is equal to I over n plus 1. Okay, so equivalently, xi is equal to f inverse of I over n plus 1. Right, so this is CDF. So if we have the n observations. Okay, so what's the smallest observation? That is, if we think about the empirical distribution function, that is approximately 1 over n, right? So we have n observations. Second smallest observation is approximately 2 over n, and so on. Right? But actually, if we think about the n smallest, that is largest observation, f of xn is n over n. That never happens because n over n is 1. So that is, infinity, right? So if f of something is equal to 1, so the inside of f should be infinity. So that's why we put n plus 1 to avoid to get xi is equal to, so this value is equal to infinity or negative infinity. So we think about 1 over n plus 1 to n over n plus 1. So in general, so this point is roughly on the straight line y is equal to x. So to see if the deviation from y is equal to x, you can see whether or not observations come from the specific distribution f. Yeah, so one example, so generate 300 random numbers from a standard normal distribution. So actually assumption is correct. Then create a normal QQ plot. Then this QQ norm of these observations makes QQ plot. It's very simple code because it's used often in statistical analysis. Then the result is here. So actually, this is actual observations. So the y-axis is actual observations. Remember that y coordinates are just ordered observations. And x coordinates are a kind of theoretical typical realizations. So f inverse of 1 over 301 to 300 over 301. So these observations. So the x coordinates of these 300 points are always the same. So if you generate a different data set, still the largest one is around 3, smallest one is -3, second smallest one is around maybe -2.6, and so on. And roughly speaking, you can see most points are on the y is equal to x. Of course, some observations, especially largest observations, it's determined by chance. But still, it's not far off from y is equal to x. Okay, so this is the typical example of the QQ plot. So in the next video, I would like to explain more examples.